Lecture 8.1, Aqueous Solutions and Precipitation Reactions. A solution is a homogeneous mixture of two or more substances. In this chapter, we will focus on aqueous solutions. The solvent is that component of the mixture that does the dissolving, which is usually present in the greatest amount. A solute is that component of the mixture that is dissolved, which is usually present in the lesser amount. Solutions can be made in any of the three major phases: solid, liquid, or gas. Solid solutions are usually composed of a solid solute dissolved in another solid solvent. Liquid solutions can be solids, liquids, or gases as solutes mixed in a liquid solvent. Gaseous mixtures are gaseous solutes mixed in a gas solvent. In aqueous solutions, solutes come in two major categories: electrolytes and non-electrolytes. Electrolytes are solutes that conduct electricity. Electrolytes produce ions by dissociation in water, making anions and cations, which can conduct the electric charge. Non-electrolytes do not conduct electricity when dissolved in water. Hydration is the process by which a solute is surrounded by the polar water molecules. Anions have the hydrogen or positive end of the water pointing toward the ion. Cations have the oxygen or negative end of the water pointing toward the ion. Non-electrolytes are different. They must have polar parts on the molecule such that the hydration process is possible. Non-electrolytes do not dissociate in water because the molecule does not break down into ions. However, non-electrolytes must be polar so that the hydration process can occur. Electrolytes can either be strong or weak. Strong electrolytes essentially dissociate 100% in water. All water-soluble ionic compounds are electrolytes. These will be determined by a set of rules which will come on later slides. All strong acids are strong electrolytes. The 7 strong acids will be presented in the next lecture. All strong bases are strong electrolytes. The 8 strong bases will be presented in the next lecture. Weak electrolytes are only partially dissociated in water. Thus, these compounds mostly stay in their molecular form when dissolved in water. Weak electrolytes include weak acids, which are any acids that are not on the strong acid list. Weak bases, which are any bases that are not on the strong base list. And slightly soluble salts, which are those ionic compounds not designated as soluble salts according to the solubility rules to be presented later. An example of a weak acid is acetic acid. It stays mostly in its molecular form with a few percent splitting into the acetate anion and the hydrogen cation, which makes it an acid. An example of a weak base is ammonia. Ammonia is a Bronsted base accepting a hydrogen ion from water to produce the ammonium cation and the hydroxide anion, which makes it a base. Again, most of the compound is in the ammonia form with a small percentage in the ammonium and hydroxide forms. Finally, slightly soluble salts, such as silver chloride, stay mostly in the crystalline lattice, with a small percentage existing as the silver cation and the chloride anion. Weak electrolytes are designated using a double arrow. This also designates that the solution is in a state of dynamic equilibrium. A dynamic equilibrium occurs when a reaction continues in both the forward and the reverse reactions, hence the double-sided arrow. Now to classify a few molecules. Sodium hydroxide is a strong base, therefore it is a strong electrolyte. Methanol looks like a hydroxide, but it is a molecular compound. We know this because there is no metal or ammonium present. As a molecular compound, it is a non-electrolyte. Next is carbonic acid. Carbonic acid is not one of the 7 strong acids. Hence, it is a weak acid, and therefore a weak electrolyte. Last, ethylamine is a weak base. Hence, it is a weak electrolyte. Precipitation reactions. This is where we will go over the rules to determine if an ionic compound is highly soluble, that is, if it is a strong electrolyte. Precipitation reactions involve ionic compounds and are sometimes called double replacement or displacement or a metathesis reaction. Precipitation is the formation of a solid when 2 aqueous solutions are mixed. Precipitation occurs when one of the potential products of the mixture is insoluble. Solubility rules for water-soluble compounds. The following rules give us compounds that are known to be highly soluble in water and are therefore strong electrolytes. The first 2 rules are absolute rules because they have no exceptions. The last 3 rules have exceptions which give us compounds that are insoluble. Rule number 1. Compounds containing an alkali metal cation, lithium, sodium, potassium, rubidium, and cesium, along with the ammonium cation, NH4+, are water-soluble. Rule number 2. Compounds containing chlorate, ClO3-, acetate, C2H3O2-, or CH3COO-, or nitrate, NO3-, are water-soluble. Rule number 3. Compounds containing the halides, chloride, bromide, or iodide, but not fluoride, are water-soluble except when combined with one of the following cations: silver, Ag+, mercury 1, Hg2, 2+, lead 2, Pb 2+. Rule 4. Compounds containing fluoride are water-soluble except when combined with the group 2 metals, magnesium, Mg2+, calcium, Ca2+, strontium, Sr2+, and barium, Ba2+, lead 2, Pb2+, or iron 3, Fe3+. Rule number 5. Compounds containing sulfate, SO4 are water-soluble except when combined with silver, Ag+, mercury 1, Hg2 2+, lead 2, Pb2+, or the group 2 metals, calcium, Ca2+, strontium, Sr2+, and barium, Ba2+. For some people, it is useful to write out all the exceptions to see what patterns arise and to become familiar with the rules better. This is a flow diagram of the solubility rules for soluble compounds. Starting at question 1, is the cation a group 1 metal, alkali metal, or the ammonium cation, NH4+? If the answer is yes, then the compound is soluble and you are done. If the answer is no, then go to question 2. Question 2. Is the anion chlorate, ClO3-, acetate, C2H3O2-, or nitrate, NO3-? If the answer is yes, then the compound is water-soluble and you are done. If the answer is no, then go to question 3. Question 3. Is the anion a halide, chloride, bromide, iodide? If the answer is yes, then go to question 3A. If the answer is no, skip to question 4. Question 3A. Is the cation silver, Ag+, mercury 1, Hg2 2+, or lead 2, Pb2+? If the answer is yes, then the compound is insoluble. If the answer is no, then the compound is soluble. Question number 4. Is the anion fluoride? If the answer is yes, then go to question 4A. If the answer is no, then skip to question 5. Question 4A. Is the cation magnesium, Mg2+, calcium, Ca2+, strontium, Sr2+, barium, Ba2+, lead 2, Pb2+, or iron 3, Fe3+? If the answer is yes, then the compound is insoluble. If the answer is no, then the compound is soluble. Question 5. Is the anion sulfate, SO4 If the answer is yes, then go to question 5A. If the answer is no, then go to the solubility rules for water-insoluble compounds. jump to question 6. Question 5a. Is the cation silver, Ag+, mercury 1, Hg2, 2+, lead 2, Pb2+, calcium, Ca2+, strontium, Sr2+, or barium, Ba2+? If the answer is yes, then the compound is insoluble. If the answer is no, then the compound is soluble. Solubility rules for water-insoluble compounds. Rule number 6. Compounds containing carbonate, CO3, 2-, chromate, CrO4, 2-, phosphate, PO4, 3-, or sulfide, S2-, are insoluble except when the compound contains an alkali metal cation, lithium, sodium, potassium, rubidium, cesium, or the ammonium cation. Rule 7. Compounds containing hydroxide, OH-, are insoluble except when the compound contains an alkali metal cation, lithium, sodium, potassium, rubidium, cesium, or barium, Ba2+. This is a flow diagram of the solubility rules for insoluble compounds. Starting at question 6. Question 6. Is the anion carbonate, CO3, 2-, chromate, CrO4, 2-, phosphate, PO4, 3-, or sulfide, S2-? If the answer is yes, then the compound is insoluble. If the answer is no, then go to question 7. Question 7. Is the anion hydroxide? If the answer is yes, then go to question 7a. If the answer is no, then the compound is partially soluble. Question 7a. Is the cation barium, Ba2+? If the answer is yes, then the compound is soluble. If the answer is no, then the compound is insoluble. A note of caution. Question 1 on slide 13 covered the possibility of the cation being an alkali metal or the ammonium cation. Answering yes to question 1 tells you the compound is soluble and you are finished with the flow diagram. Thus, questions for the alkali metals or ammonium cation are not necessary in the flow diagram for the insoluble portion, questions 6 and 7. Classify the following as soluble or insoluble in an aqueous solution. Barium nitrate is soluble according to rule number 2. Silver iodide is insoluble according to the insoluble exceptions to rule number 3. Calcium sulfate is insoluble according to the insoluble exceptions to rule number 5. Magnesium hydroxide is insoluble according to rule 7. Sodium chromate is soluble, according to Rule 1. For aqueous reactions, we have three different ways of representing the chemical dynamics that take place in the reaction. The molecular equation shows all the compounds present by their molecular formulas, and the reaction is balanced and contains state symbols. The total ionic equation shows the dissociated form of electrolytes, especially strong electrolytes, in the aqueous state. Compounds that are solids, S, liquids, L, or gases, G, do not dissociate in aqueous solutions. Thus, these compounds are left in their molecular form. The net ionic equation shows only the reacting chemical species by eliminating common ions from both the reactant and product sides of the reaction. The reaction on this slide is lead-2 nitrate reacting with sodium iodide to make lead-2 iodide and sodium nitrate. The molecular equation shows all reactants and all products in their molecular form. Lead-2 nitrate, sodium iodide, and sodium nitrate are all soluble in water and therefore have an aqueous state designation. Lead-2 iodide is insoluble, thus it is in the solid S state. To make the total ionic equation, all ionic aqueous compounds are split into their ions. When this happens, subscripts become coefficients. Lead-2 nitrate contains one lead ion and two nitrate ions. And that is how it shows in the total ionic equation, with the nitrate ion having a coefficient of 2. The two sodium iodide molecules split into 2 sodium ions and 2 iodide ions. On the product side, the 2 sodium nitrate molecules split into 2 sodium ions and 2 nitrate ions. The lead-2 iodide on the product side is a precipitate as designated by the S for solid. Thus, lead-2 iodide remains in its molecular state, not being split into individual ions. Thus, the total ionic equation reads lead-2 aqueous plus 2 nitrate aqueous plus 2 sodium aqueous plus 2 iodide aqueous yields lead-2 iodide solid, the precipitate, plus 2 sodium aqueous plus 2 nitrate aqueous. Common to both the reactant and the product sides of the reaction are 2 sodium aqueous and 2 nitrate aqueous. These are removed to form the net ionic equation, which reads lead-2 aqueous plus 2 iodide aqueous yields lead-2 iodide solid. In essence, The net ionic equation represents the underlying chemistry that occurs. The sodium and nitrate ions are designated as spectator ions. Spectator ions do not participate in the underlying chemistry, and other soluble ions could be exchanged and get the same result. For example, any of the alkali metals could have been the cation for the iodide. Also, acetate or chlorate could have been used instead of nitrate as the anion for lead. To get to the net ionic equation, follow this outline. First, write a balanced molecular equation with the state symbols on all chemical species. Second, separate all strong electrolytes, that is, ionic compounds designated as aqueous, into individual cations and anions on both sides of the reaction equation. Remember, keep polyatomic ions intact. Finally, cancel the spectator ions, that is, aqueous ions that are common to both the reactants and the products. First, write out the reactant side of the equation, which is AgNO3 aqueous plus NaCl aqueous. Second, swap the cations, making sure that the products are ionically balanced. The products here are sodium nitrate, NaNO3, and silver chloride, AgCl. Balance the equation. This one is already balanced. Determine if either of the products is insoluble. NaNO3 has sodium in it, so by Rule 1 it is soluble and gets an AQ. By Rule 3, silver chloride is an exception to the chlorides being soluble, hence AgCl is a precipitate and gets an S. The final balanced molecular equation is AgNO3AQ plus NaClAQ gives NaNO3AQ plus AgClS. Next, all the aqueous ionic compounds are split into cations and anions. This yields the total ionic equation. Ag plus AQ plus NO3 minus AQ plus Na plus AQ plus Cl minus AQ yields Na plus AQ plus NO3 minus AQ plus AgClS. Comparing the reactant and product sides, we can see that sodium and nitrate are common to each side. These must be the spectator ions, leaving the net ionic equation Ag plus AQ plus Cl minus AQ yields AgCl S.